Hello all. Today we will talk about a few of the variants of queue data structure. So let's start with a circular queue. To better understand the concept, let's have a look at the problem which we have already discussed during the simple queues. As is shown here, the queue it is full right now. Hence, the front pointer is 0 and the rear it is at index 4. Now, the continuous execution of the dequeue operation will keep on updating the front pointer, and finally we will reach a situation where front exceeds the rear pointer, which thus marks the underflow condition. Now, here comes the contradiction, as the queue is both underflowing as well as overflowing. It is underflowing as the front it exceeds the rear pointer, and it is overflowing because rear is pointing at the maximum index available in the array. Moreover, we can observe that there is a space to add more elements to the queue, but due to the condition which we have framed for simple queues, we are not able to use this space. So the idea is to join the front and rear ends of a queue, and the resultant structure is termed as a circular queue. Everything remains same, but the conditions for the underflow and overflow are rewritten as is shown here. For overflow, we are checking if front equals to rear plus 1 modulus maximum capacity of the queue, and for underflow we are checking that both the pointers, that is front and rear, they both should be equals to -1. Let's have a look at an example now. As is shown in the current slide, that the circular queue it is underflowing. Therefore, front as well as rear pointer, they both have value -1. Now, if we keep on enqueuing elements in this circular queue, then after 8 insertions, the queue gets full. And now we have reached the overflow state, and hence the equation front equals to rear plus 1 modulus 8 gets satisfied. The positions of front and rear pointers may be any, as is shown in the two figures at left and right hand sides. Next, we will discuss how to update the front and rear pointers. So, let's say at any moment of time, we have a circular queue like this, as is shown in the current slide. Here, front it is equals to 4, that is, it is pointing at index 4, and rear it is pointing at index 7. When we insert a new element, then this rear it has to be updated. So we have to increase it by 1, and 7 plus 1 will give us 8. But the allowed indices are ranging from 0 to 7. Therefore, the rear pointer has to be updated using an equation rear equals to rear plus 1 modulus 8. In a similar way, if we talk about the front pointer, then in the shown example, when we perform a deletion operation, the front it has to be updated using the equation front equals to front plus 1 modulus 8. Thus, front will get updated to 0 after the deletion. Here is the algorithm for Dequeue operation in circular queues. First, we have to check for the overflow condition at line number 1. If queue is not full, then we have to simply update the rear pointer to rear plus 1 modulus maximum capacity of the queue, and the same has been done at line number 4. Then we have to put the element at the rear index at line number 5. Also, if the circular queue is empty, then front pointer has to be updated to 0 in addition to the rear pointer during the Dequeue operation. Otherwise, the Dequeue operation it will only update the rear pointer and not the front pointer. In a similar way, we can write an algorithm for the Dequeue operation on circular queues. Again, first we have to check for the underflow condition. If circular queue it is not empty, then we just have to update the front pointer as is done at line number 8. We are updating front to front plus 1 modulus maximum capacity of the queue. Also, if there is a single element in the circular queue, then we have to update both the front as well as the rear pointers, and they are required to be updated to -1 as is done at line number 6 here. Rest all the other functions can be implemented using the similar procedures as we have discussed in simple queues. We just have to modify the Unqueue and Dequeue operations, and we have to update the conditions for underflow and overflow in order to implement the circular queues. The next variant is the doubly ended queues, which is a generalization of queue data structure. The task of enqueuing as well as dequeuing, they can be performed at either of the two ends in a dequeue data structure, which thus provides it the capability to be used as a stack as well as a queue. Dequeue, it is of two types: an input restricted dequeue and an output restricted dequeue. Input restricted mean we are putting restrictions only on the Dequeue operations, that is, we have to fix one of the two ends for insertion. However, dequeue or deletion it may happen from both the ends. Similarly, when we say an output restricted dequeue, then we are limiting dequeue operation at one end only and allowing insertion, that is enqueue, at both the ends of the queue. Next variant is the priority queues, where all the elements in a queue has an associated priority, and this priority has to be taken care for during the insertion and deletion operations. In case there exists more than one element having same priority, then we have to follow first come first serve order. One can give more preference either to lower values or to upper values. Accordingly, there can be two types of priority queues, a min priority queue and a max priority queue. Min priority queue means lower is the value, higher is the priority, and vice versa is the case when we work with max priority queues. That is, higher the value, higher is the priority. Here we are talking about priority queues which are implemented either using arrays or linked list. Therefore, the priority queue can either be ordered or unordered. In unordered, priority is not considered during insertion and and insertion can happen at the end, whereas in case of ordered, insertion has to take place correctly as per the priority, that is min or max. Though priority queues can be implemented in this way, but they are optimally implemented using a heap data structure, which will be covered later in this course. So here we are skipping the implementation details of the priority queues either using arrays or using linked lists. Let's have a look at an example now. And with this, we are going to end this session. Here we are assuming that an array is used for implementation of the priority queues. We may have an unordered or ordered version of the priority queue, and here in the ordered version we are going to maintain the priority using the ascending order at any moment of time. Also, whenever an element in case of an unordered version has to be deleted, then the last element will be used for replacement instead of shifting all the array elements by one position as we have seen in case of arrays. So here the first element which is inserted is P. Then we have inserted Q. In unordered version, Q is inserted at the end. Also, as per the ascending order, Q should be placed after P, and the same is done here. So, Q is inserted after P in ordered version also. Then we have to insert E. In unordered version, E is inserted at the end. However, in case of ordered version, E is inserted before P as well as Q. That is, E is inserted at the first position. Next, we have removed maximum element in the queue. Now, in case of ordered version, the last element will be deleted directly. But in case of unordered version, one has to first search for the maximum element and then the maximum element has to be deleted by replacing it with the last element in the queue. Next, we have inserted three more elements X, A and M in the queue. In case of unordered version, these elements get inserted at the end of the queue as is shown here, but in case of ordered version, X, A and M are inserted at their correct positions. Lastly, we are removing the minimum element in the queue. So again, In case of ordered version, the first element, that is A, will be deleted directly, and in case of an unordered version, element A has to be searched and then it has to be replaced with the last element in the queue. So this is all about the variants of a queue data structure. After understanding the concept of these variants, you may try to implement these data structures. Thank you.